Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the last exercise video, we practiced identifying which OLS assumptions failed by looking at the graphs because the data gives us hints about patterns that we should be aware of. In this video, we're going to concentrate on a few typical graphs that you see a lot in the books, and it might be a little bit difficult at times to understand them and especially reproduce them when you're asked to show like what would have happened or how could you show that actually an OLS assumption has failed. So in this video, we're going to look very carefully at 4 graphs, especially related to homoskedasticity assumption and to the distribution of the error term assumptions to see how exactly they play out and what kind of interpretation should we give when we see them. This is the first graph. Try to pinpoint by yourself all of the elements that you see. And just for comparison and reference, have a look at the second graph as well. So you will see you're given the relationship between x and y. You have the estimated line in there. Most of the times you'll see that actually they don't have the hats in here. It's completely fine. What we're saying is this is the population one, and we've done a very good job with our OLS to getting to the actual population parameters. We see at the same time these vertical lines in here. Now keep in mind, every dot in this graph would be a combination of coordinates of x and y, an observation. So in a sense, all of these vertical graphs, like vertical lines in here, they are clouds of possible y values that you would see. Okay? And then these are sort of like the clouds as well. In this first graph, the clouds are the same everywhere. It's a little bit easier to see, especially when you compare the second graph, where very clearly these clouds are not really the same everywhere. Now, what does this first graph tell us? It's showing us the conditional distribution of y given x. So the red line, the conditional mean, is going to tell us that the expectation of y on x is equal to basically beta null plus beta 1x. The vertical spreads, think of them as the representation of the error term. The same spread everywhere means that we have the variance of the error term conditional on x being equal to sigma square. So most of the times, I'll add one more element. When you see this graph, actually, for all of these, you'll have the error term showing in here as well, okay? So if you want to recreate this, and this is a good way to show homoskedasticity, you can easily do that by just creating one of these like clouds or distributions and then just copy pasting it everywhere the same, and you've shown that the spread is everywhere the same, so the variance of the conditional variance is sigma square, meaning you've got homoskedasticity. Now, what about the heteroskedasticity case? So obviously, this is the heteroskedasticity case. In this particular instance, that means that the conditional variance is not going to be sigma squared, because obviously when x is has a value of x1, we've got a different distribution here, and when we've got the x2, a different distribution, and x3 exactly the same. So keep in mind, the problem that is created through this is not going to be the bias, okay? So the problem is not bias, but precision. Because here conditional variance is not sigma square everywhere, which means for smaller values of x1, you see smaller noise, but x2 here, look, this distribution has quite very long tails. You've got a very big spread. You see a lot more values of y when you go there. So it's not going to give you what the same. Let's move to the next set of graphs. In here, we're looking mostly to the distribution of the errors. Remember, according to assumption 7, we said that they are normally distributed, although it is very unlikely that we will see that in real life and prove it. If we use the central limit theorem and the sample size is big enough, then we can make an approximation that they are normally distributed. Now, what each of these curves is now representing is obviously, for the first graph here, very clearly a normal distribution, very symmetric. The red line, again, is a particular value of the y that we are going to look at. So it's not the OLS estimation, just like a particular line y value that we see. Some observed points, which I have done in more bolded. So what we see is that under normality, you can see there are some extreme values that are possible, but for instance, this particular one right here is not that likely. So even though it's very far compared, especially to these two, there is a chance, there is some probability that we observe it, but it's a bit unlikely. The further, in fact, you go into the tails, the less likely it is that you will see these kind of values. And again, we're not talking about bias or variance in here. We're talking about likelihood based on this distribution. Now, for the non-normal error terms in here, extreme values are more common because, look, if this was in the tails in the first example and the mean would have been where the red line is showing, in this particular second graph, we can see that, well, you see in here, this where the mean should be falling. So now this value that was not so likely to happen when we had the normal distribution, even though it was extreme, well, now it's extreme and it's a lot more likely to happen. What does this mean? So when you have heavier tails, when you have skewness or both, under these kind of error distributions, larger deviations from the mean are more likely to happen compared to the normal distribution that we saw. And this will directly affect small sample inferences, t-test, confidence intervals, and so on. So keep in mind, you'll always have to deal with graphs, and it's very important that you understand what exactly these graphs are trying to teach you. What are the hints that the data is trying to give you? They are also, in a sense, maps from assumptions to the data. So if you learn to read them, you can diagnose problems before running tests and also have an understanding why a method will work or fail already. Hope this was helpful, and I'll see you in the next video.